Okay, in this video we're going to take a look at inverse trig functions. We'll introduce them, and then in the next video we'll look at some examples of finding the actual values of inverse trig functions. So recall that for a function to have an inverse, any horizontal line we draw through the graph of the function can hit the graph of the function at most only one time. So this is going to create a problem with our periodic functions, such as y equals the sine of x, because here we have y equals the sine of x in blue, and we have the horizontal line y equals a half in red. And notice that this horizontal line hits the graph. In this graph, it hits it 4 times, but because it has this periodic nature to it, if it hits the graph once, it's automatically going to hit it an infinite number of times. So we have a bit of an issue with the horizontal line test and our trig functions, the graphs of our trig functions passing it. Now, again, bear in mind that horizontal line tests and inverse functions, for inverse functions, if we know the value of the angle, we can plug it in to get the ratio. Inverse functions allow you to know the ratio and figure out what angle gives you that ratio when you plug it into the function. So in order for this thing to pass the horizontal line test, we're going to have to limit the graph to a smaller domain. So in fact, all of our trig functions are going to fail the horizontal line test. So if we restrict the domain on each of them, we can get it and manipulate it to actually pass the horizontal line test and have an inverse. So for our sine function, if we limit our domain to be between negative pi over 2 and positive pi over 2, then any horizontal line we draw is going to hit this graph at most one time. And typically with trig functions, we try to get the domain restriction to be somewhere around the origin if possible. So the inverse of y equals sine of x is y equals the inverse sine of x, where again we're using this inverse notation between the function and the argument, like f inverse of x. It does not mean raising sine to the negative 1 power. That's what cosecant is. In order to avoid that, we have an alternative notation for it, and that's putting the prefix arc in front of the trig function. So sine of x, its inverse would be arc sine x. Cosine of x would be arc cosine x, etc. And again, bear in mind, when we take the inverse, we reflect the graph across the line y equals x. So our x's become y's and our y's become x's. The domains and ranges trade places. All that stuff we talked about in with inverse functions a while back. So here we have our inverse sine of x function. Notice the domain is between negative 1 and 1, which is the range of our regular sine of x. And our range of this inverse function is negative pi over 2 to positive pi over 2, which was the domain restriction we had to place on our original sine x graph. So here we have I'm going to list out a table here for the 6 inverse trig functions with their respective domains and ranges. And in the next video, we'll take a look at some examples. So we saw already for inverse sine, its domain, its input, negative 1 to 1 inclusive with both of those. Output values between negative pi over 2 and positive pi over 2. So we can input any value of x we want as long as it's between negative 1 and 1 inclusive. And our outputs are going to be between negative pi over 2 and positive pi over 2 inclusive, or between negative 90 degrees and positive 90 degrees inclusive. For inverse cosine, our domain will be the same as our inverse sine. And in order for cosine to pass the horizontal line test, we would restrict the cosine graph to be between 0 and pi, which means that's going to be the range of our inverse cosine is between 0 and pi. So just like with sine, we can input any value for x between negative 1 and 1 inclusive, and the values we're going to get back are between 0 and pi, or 0 and 180 degrees inclusive. For inverse tangent, our domain is all real numbers. If you look at the graph of tangent, its range is all real numbers, so our domain of our inverse tangent is all real numbers. Now, because tangent has vertical asymptotes at odd multiples of pi over 2, we can't use brackets at negative pi over 2 and positive pi over 2. We have to use parentheses because there are vertical asymptotes at the tangent of pi over 2 and tangent of negative pi over 2. So if you see the parentheses, that typically means that there's a vertical asymptote there for the original function. Inverse, or the reciprocal rather, of sine is cosecant. So cosecant, we can input any number less than or equal to -1 or greater than or equal to +1. We're going to get back any number between -π/2 and +π/2, but we will not get back a 0. So that explains why we can't get 0 in return for our cosecant, inverse cosecant. For inverse secant, has the same domain as inverse cosecant, less than or equal to -1 or greater than or equal to 1. This time our outputs, kind of like with cosine, between 0 and pi, but because we have a vertical asymptote for secant of π/2, we can't equal π/2 for our outputs for inverse secant. So, and again, same thing with the cosecant and sine. Notice the difference between them is with cosecant, it can't give us back a 0, and with secant, it can't give us back a π/2. And finally, cotangent, just like tangent, our input is all real numbers, and our outputs are going to be between 0 and pi, non-inclusive because of vertical asymptotes for a cosine of 0 and or cotangent of 0 rather, and the cotangent of pi. So that's why there's parentheses associated with those values for the range. All right, that about does it for this video. Thanks for watching. I'll see you next time.